Speaker tonight is Al Taylor, who's going to talk about the Maryland IP network. And I had asked Al to do this because although I'm from Cape Cod, I have belong to a club in Maryland. Have an alternate site down there at my daughter's house. And Al had given the presentation to that club, which I saw, and that inspired me to get involved with my club. And we've now formed something called the Cape and Islands Emergency Communication Network. And I can blame Al for that. Was impressed with his presentation, and I was hoping that he would do something for us, and he agreed to. So I'm very happy to have him here. So Al Taylor.
We should be good to go, right?
Yes, you are. I gotta get rid of Lim, but you're good to go.
To everyone, or if you're listening to this by the recording, who knows? Good morning. So, one of the fringe benefits of doing this kind of work is we get to go to places where the view is pretty good. So this is just one of the sites where we have our equipment. We're in Rockville, Maryland here, looking north, and the ridge at the horizon there is about 40 miles. If we turn 90 degrees to the left, we can see the Skyline Drive or the Blue Ridge Mountains of Virginia, about 50 miles distant. So on a clear day, you can see pretty well from up here. It's the tallest building in Rockville. And Rockville itself is only a few hundred feet above sea level. So it's not saying much, but we're above average terrain anyway. Let's see if I may have to click here to get the, I just clicked the bar to get to the next slide and nothing happened. So let me see what I have to do to. Well, that worked. So if you're watching this after the fact or looking at the PDF version of the slides, up in the top left corner of your screen, you should see a little icon. And if you hover or click on that icon, depending on your PDF viewer, you'll be able to see the speaker notes that I've put into these slides. I tend to say things that I try not to read the slides, put it that way. So the speaker notes will kind of fill you in with some of the information that I'm going to share tonight that's not actually on the slides. So moving along, I'm going to talk about the Mid-Atlantic IP network, and I'll tell you a little bit about the network itself, how we got this project going, how we arrived at the network architecture that we're working on right now, and why we did it that way. And then, in case some of you are interested in creating a network like this, I'll talk about some of the difficulties we encountered. But before I do that, I want to say a few things that I'm not going to do. So I'm not going to brag about our wonderful network. In fact, after several years of effort, our lack of progress is really frustrating. It seems like we should have gotten further than we have, and I'll try and be honest about that. So we started with a vision for fulfilling an unmet need. We have learned a lot about what's required to build a microwave network, and we believe that we've demonstrated the feasibility of our approach. And in some ways, I've been very surprised at what this equipment can do. It exceeded my expectations, I'll say that. But there's a lot of work remaining to achieve the vision that we've set for ourselves. And I have to tell you also that unlike a lot of Red Pack presenters, I'm not an expert in microwave networking. I'm not an exceptionally gifted speaker either. You're not going to find me giving a TED talk anytime soon. As Lem said, he heard me give this presentation at a local club here in the Baltimore, DC area, and he thought it would be of interest to a wider audience. When he first spoke to me, I thought he had in mind my talking to his group on Cape Cod, and I was very surprised to find myself listed on the Rat Pack website as a speaker, because you know, a lot of the folks who have do presentations on RadPack are way above my level in terms of expertise in their topics. So just to be clear, my primary ham radio interest is in disaster communications, and I do have actually a lot of experience in that field. I worked full-time for several years with the National Disaster Medical System back in the 1990s, and I've been to quite a few disasters as a federal responder. I started out as a volunteer locally in the DC area. After my stint as a professional federal disaster responder, I'm back to being a local volunteer in the DC area again, and so I've come full circle. So I hope this will be a down-to-earth presentation. And I really want to start off by saying that MAIPN was started by a small group of hams led by a fellow named Keith Elkin, KB3 Tango Charlie Bravo, who I like to describe as the Johnny Appleseed of amateur radio broadband networking in the Baltimore, DC area. Keith started seeing what this technology was good for before anyone else was aware of it. And he and his wife, Eva, who they're both software developers, you know, by profession. So she's as technical minded as he is. And they started traveling to ham club meetings all over the area and to promote exploration of this technology. And Keith was just tireless in his experimentation. He was newly retired, and he really jumped into this with 3 feet. So my first involvement with Keith was in 2014, by which time Keith and Ava were already going strong. At some point, they hooked up with a fellow named Dick Heyman, WN3R, who helped to formulate what became the MAIPN concept, MAIPN being the Mid-Atlantic IP network. And MAIPN incorporated as a 501c3 nonprofit in 2015. And Keith also had an article on high-speed networking published in QST that year. So as I say, they were going strong and right about the time that I joined in. Unfortunately, we would have wished that MAIPN would have grown, and we did attract a number of people to work with us, but for one reason or another, and health reasons have been a big part of it, we've lost some of those key people. And then Keith and Eva decided to move to San Francisco to be closer to daughter and granddaughter. So when they left, MAIPN really became a much smaller organization because of all the energy they were putting into it. We really miss them, but we know that they're happy being out there. So again, what I'm not going to be talking too much tonight about all the different options that are available. So there's groups of hams across the US and beyond doing similar kinds of things with wireless broadband equipment. And these are some of the efforts you might have read about in QST or on the internet. There's a wide variety of approaches and possible applications for this equipment. And I'm not really going to go into the big picture. I'm only going to talk about what we decided to do and why. So we're a group of hams who set out to develop, our real focus was disaster communications capabilities in the best spirit of amateur radio. And our primary goal is to build a fixed network linking emergency operating centers and hospitals throughout the DC metro area and beyond. And by beyond, we certainly mean the Baltimore area and as far as we can get. And the interesting thing about that is, though we are hams, the network that we're using is not using, for the most part, ham radio frequencies, where we made a decision to use Part 15 equipment, and I'll explain that as we go along. But we do have in mind that we can use this equipment for some purely ham radio applications, like establishing repeater links, and I'll talk about that too. One of the things that we don't do is we don't encourage individual hams in our service area to connect to the network for the purpose of making contacts and rag chewing. There's better ways to do contesting than using the equipment we're using. Our focus is on serving disaster organizations and ham radio infrastructure, if I can put it that way. So one of the decisions we made early on is the backbone of the MAIPN network, the primary links that connect across our region. It's the biggest part of the mission. But another thing that we'd like to do, where possible, is to develop a capability to project broadband service to arbitrary locations within the MAIPN service area. And I'll touch on that too as we go along. I want to talk now about the network architecture we arrived at. And I think it helps to start from network architectures that you might be familiar with. So, you know, one thing that we're not is a cellular network. And you all know what a cellular system is, so I'm not going to dwell on that. If you want to look at the slides later, I have a few more kind of salient points about what a cellular network looks like. But let's just move on for now. We all know what cellular is. So a lot of people, as soon as they hear what we're doing, they say, oh, so you're doing mesh, right? Well, actually, no, we're not. So a good question is, why not? So let's take a look at this for a minute. So a mesh network is a network of specially configured wireless routers attached to radios that are sited in a limited contiguous geographic area. And every node in the network has to be within earshot of at least one other node. And to have a reliable network, you ideally want to have each node within earshot of 2 or more nodes. Generally, in most mesh networks, all of the nodes operate on the same frequency or the same channel, or a very limited set of reusable channels. And these nodes self-configure into a network. Nodes can freely join or leave the network. And there are quite a few commercial mesh network protocols that have been developed for various applications in building automation, industrial and agricultural applications, and so forth. Okay, so let's not get ahead of myself here. All networks exist to enable users to convey information from one location to another through one or more intermediate nodes. Okay, so the key to any broadband network is the routing algorithm for routing that information from one node to the other to get from point A to point B. And in a mesh network, each node maintains a map showing which nodes can talk to which other nodes. And the individual nodes use this map to determine the path that any traffic should take to get from an end user at point A to another end user at point B through the network. So the routing algorithm in a mesh network is almost always implemented directly in the radio, or a box that's attached to the back of the radio, basically, along with the data protocols and the modulation scheme that's used over the RF link. So that's what distinguishes a mesh network from other network topologies, where in most other network topologies, the routing of packets through the network is carried out by a separate box, surprisingly enough, called a router. So everyone here that's on the internet has a router in their home, which is performing this function of routing messages from computers on your home network onto the wider internet. And in a mesh network, as I said, the routing algorithm is almost always implemented directly in the radio, along with the protocols. And oh, I think I just said that, didn't I? In a mesh network, each user device connects directly to the radio with its built-in routing algorithm, usually by Ethernet cable or Cat5 cable. And the router might be needed to serve as a gateway at a node where the mesh network is connected to the internet. But as long as the data is remaining within the mesh network, there's no separate router necessary other than the one that's built into the radio. And theoretically, a mesh network is simple to set up and administer. In most designs, you introduce a new node into the network simply by turning it on, and it announces its presence to any other of network nodes that are within listening distance. And if it finds anyone to talk to, then this information about its presence is shared with the other nodes so that they can all add this new node to their network MAC. So the self-forming characteristic of a network is really attractive for building a network out in the field. And it also means that the network is self-healing, right? So if node 2 up in the top left corner there fails or goes off the air, the routing algorithm finds a new path through the network, so from A to B. And to maximize its efficiency, the routing algorithm or protocol tries to choose its path with the minimum number of hops. Some mesh networks can also take into account the data throughput on individual hops, bypassing links that have a slow connection speed or really heavy traffic, for example. So it might take a slightly longer path through the network in order to get around a link that's carrying a whole lot of different traffic for different endpoints. So like a lot of hams, the folks who started MAIPN, Keith and company, we started with the surplus Linksys routers, and that had custom mesh networking firmware installed on them. And we quickly found that these things are completely unusable in the urban suburban environment beyond a few hundred yards, even with a high gain directional antenna. We tried to do a link between two of these with high gain antennas just a few blocks apart, but there are still 45 houses in those few blocks, all of them running Wi-Fi on the same frequency. And that with that level of interference, it just wasn't going to work. So very quickly, the folks who developed this mesh protocol went from using these Wi-Fi routers, very low power, designed for use within a single home, to using equipment like the sector antenna and the dish antenna that you see. And they ported the mesh software to those devices and got a lot further with it. And, I could talk all night, but we're already 20 minutes into the hour. So I'm going to skip this slide, but probably a lot of you are already familiar with mesh networking. If you're not, you can certainly pull up the slide deck afterwards and have a look in more detail. So that's something that we're not doing with MAIPN. And so now finally, I'm going to talk about what we are doing. So let's take a look at a basic office local area network. And let's say you have a business that occupies several floors of an office building. You install a LAN to provide a variety of network service to your employees throughout the building. The network is based on switches that are usually located in data closets on each floor of the building. The switches are all connected by fiber to servers in a central location. And the server farm, if you will, hosts your voice over IP telephone system, your email server, and other business applications that you might be using, as well as providing access to the internet through a corporate firewall. And all that stuff happens in the network center. And a network like this can also be extended to other nearby buildings and cover an entire campus using fiber optic links between the buildings usually. So it doesn't stop there. Suppose you have facilities scattered around town and you want to have total control of the sensitive data on your business network. So you might pay an installer to install a dedicated fiber optic run from one of your corporate locations to another one a few miles away. And so everything is still linked up by fiber optic cables to your server farm. And so it's still as far as your user is concerned, it's still a local area network. But when it extends to distant links that are more than a stone's throw away, the term of art in the networking community is Metropolitan Area Network instead of Local Area Network. So the acronym is MAN instead of LAN. So you can go further than that, and let's say you have other facilities in other parts of the country. So what you do now is set up using a VPN or virtual private network technology. You set up virtual links through the internet over these encrypted channels that link one of your facilities to another one in a distant facility. And now you have what's called a wide area network, or a WAN. And the difference between a WAN and a MAN is the use of the internet as a medium for making the connections to those sites that are too far away to run fiber optics to. Okay, so we have LANs, MANs, and WANs. And so here's yet another alternative to building a metropolitan area network. Instead of running fiber optic cables across the river to a campus on the other side of town, what if you could put a microwave dish on the roof of the buildings? As long as you have line of sight, you can route your IP traffic between those two campuses over the microwave radio channel. And each pair of dishes pointed at one another is effectively a Cat5 cable or an IP network I'm sorry, it's effectively a Cat5 cable or a fiber optic cable, and you're replacing copper wires or glass with a microwave data channel going between two dishes. And so that would work. It sounds pretty expensive, but it turns out it's a lot less expensive than you thought. So that's the approach taken by MAIPN. MAIPN is essentially a private, non-commercial metropolitan area network linking hospitals, EOCs, and a few other served users. Repeater sites, for example. Okay, so let's talk now about the equipment. So here is a dish sitting on basically attached to a fence in somebody's backyard. That particular unit is made by a company called Ubiquity. The model is NanoBeam M5, standing for the M5. The 5 stands for 5.8 gigahertz. It costs just $70. You get a self-contained digital microwave radio built in to the feed horn of a dish that has 19 dBi gain, and it runs up to close to a watt of output. So 19 dBi over approaching a 1 watt signal means your effective radiated power can be pretty high in a narrow beam width. So a pair of dishes like this, pointed at each other over a clear line of sight path, can sustain a data rate of roughly 300 megabits per second, and that's split up both directions. So if you're running effectively full duplex, you can get 150 megabits per second in each direction, or by how you program the radio, you can put 250 megabits in one direction and 50 megabits back the other way. Depends on what you're trying to do. The radio built into the dish and its attached computer with the routing algorithm is powered by a 24-volt DC power supply over the same Ethernet cable that carries the data. So if one of those radios is plugged into a computer or a standard Ethernet switch at either end of the microwave link, it's exactly as though those switches or computers are connected by a gigabit class Ethernet cable. So basically all I'm saying is we can use a pair of dishes like this to extend the reach of a local area network over distances that span a metropolitan area, as long as you have 2 points with a line of sight between them. We can use this network link for any application that can be run over a normal office local area network. And that's one of the killer apps for this equipment. A lot of most of the people who buy this equipment are actually operating internet service provider companies, often in smaller communities that, you know, the big companies don't want to bother with. And they set up these radios to deliver Wi-Fi to paying customers in their homes or businesses. But as I said, you can use these radios anytime you want to network two different sites without running a cable or a fiber between them. Okay. So that $70 dish that I showed you works amazingly well. For just $30 or $40 more, you get a 2-foot diameter dish with a 30 dBi gain instead of 19 dBi. You pay a little bit extra for the shielding kit here that surrounds the dish, mostly to reduce interference from the side and to focus, focus the listening in the direction of the dish. With this much gain, the beam width is about 10 degrees, which is narrow enough to cut out of a lot of potential interference out there. But it's wide enough that it's relatively easy to point two of these things towards each other. You don't need a telescope or to aim them. You can point in the general direction. You can pick up a signal and then just tune for maximum signal strength by rocking it back and forth and up and down. So it's really easy to aim these. The bigger the dish, the harder it is to aim them in the direction of at the other end. So a pair of dishes like this can work up to over a 50-mile link, or with a throughput of up to 450 megabits per second. But you won't get that much throughput over that long a distance. They're more likely to be used over a 5 to 10-mile link, where you can get full throughput. The longer the length, the lower the throughput, because the lower the signal to noise ratio and the more errors you get. But we use a dish in this size and price range because, number one, we can afford them, and number two, they provide the right amount of capability. And as I said, they're relatively easy to set up. A 4-foot dish weighs 10 times as much, and it's a lot harder to wrestle with on the top of a tower or a mast. These two people can easily set one of these things up practically anywhere that you can get to. I mentioned earlier that we chose to use Part 15 frequencies instead of the ham radio bands. So we're among a number of network developers we're aware of who made that decision. And most of us are focused primarily on the 5.8 gigahertz band. And this was really a contentious choice, a lot of debate to get to this point. And I was among the people who needed to be convinced to take this approach. So the rationale is that by using Part 15 frequencies, our served agencies can use this network without the need for a licensed ham to be on the site serving as a control operator. And they can encrypt their sensitive traffic, which can't be done under the Part 97 rules. The flip side of that is that since we're on Part 15 frequencies, we have to accept any interference we receive from any other Part 15 users. And we have to follow the rules about, the maximum amount of effect of radiated power and the maximum amount of bandwidth and so forth. But the equipment we're using takes care of all of the equipment we're using and forces us to follow the Part 15 rules, which makes that part of it easy. And, there's huge benefits for our anticipated customer base if we're using Part 15 frequency. So that was our decision, for better or worse. And that, the interesting thing is now we have a bunch of hams building communications equipment for served agencies, but it's actually not ham equipment for the most part. Now, we do have an exception that if we're serving a remote repeater site, which is purely a ham radio end user, we will use a 3.6 gigahertz part 97 frequency for that on-ramp or off-ramp from our backbone network. But if there's any chance of some of our non-ham customer base wanting to use the network, then we stick to part 50. Now, in the beginning, I was really convinced that with all of the Wi-Fi equipment already on 5.8 gigahertz, that we were going to have enormous amounts of interference, and it just wasn't going to work in our urban and suburban environment. It turns out that at the sites, like I showed you on the front slide, we're way above all of that other stuff. And the interference, you can, if you look with the spectrum analyzer, you can see lots of home Wi-Fi routers on the air, but the signal level is really low. Since we're following part 15 rules, we're not interfering with them, and they're not interfering with us because we have enough signal strength that we view all those other users as noise, and our signal to noise ratio is 15 to 30 dB. So they're not really affecting us at all. Now, there is equipment available on the commercial microwave bands. There are some part 15 microwave bands up around the 60 gigahertz region. That equipment still costs a lot more. So we're not using any of that stuff. But if we ever had a need for a super strength link, we could consider using some of that equipment to go over a very long distance, or if we need a high throughput pipe, we could use some of that stuff. But so far we've not needed to, and we certainly haven't been able to afford to. So that's the general idea. There's just a few more features of this equipment. Instead of using these dishes, which are highly directional for point-to-point links, we can use a sector antenna, which then allows multiple point-to-point antennas to connect to the same node. So then the bandwidth of that channel is now being shared with 2 or 3 endpoints. But if we're talking about 450 megabits per second divided 3 ways, 150 megabits per second is not too shabby for a lot of different applications. We have used the network, for example, to run Zoom meetings. So certainly the network will support some reasonably high bandwidth applications. So here's what the network actually looks like, kind of in a schematic form. We're showing here a 4-node backbone, but the network can be extended to many more nodes than this. At each backbone node, there are 1 or more digital microwave radios that establish point-to-point links or point-to-point multi-point links with other nodes or endpoints. And these radios are connected to a Cat5 by a Cat5 cable to a backbone router, which is the pink rounded rectangle you see at each of those nodes. And unlike in a mesh system where the router is built into the radio usually, this router is usually a separate hardware item. And we use a commercial router made by a company called MikroTik. And the routers cost about a little over $100 each right now. At least one other group that I know of is doing the same thing, is using surplus Cisco routers in their network. And it's actually the programming of these routers that establishes the topology of the network, not the programming of the radios. The radios software controls the modulation scheme and error correction, but the routing is done by a hardware router. And at some of our tower sites, the router is actually in a weatherproof box, just bolted onto the base of the tower, down at ground level where we can work on it. On the buildings, the router is usually in the penthouse of the building. In some cases, we put it outdoors. And the router requires, depending on which model we use, either 24 or 48 volts DC power. which we either get from a wall wart or, uninterruptible power system. And the router feeds power to the radios over the Ethernet cables. So unlike a mesh network, which forms itself on the fly, in one of these networks, which the trade name for the network protocol is AirMax. In an AirMax network, anytime a node is added to the network, manual effort is needed to program the router to establish the links to adjacent nodes. And in the event of a loss of node, the routing algorithm that we put into the router attempts to reroute the traffic to an alternate path if there is one. So the routers can have some pretty sophisticated software, but all that programming has to be done manually in our network. And in the interest of time, let's just move on. So here is a map of the DC Baltimore region, and what I'm showing you here is all of the links that are currently operational. The dashed line links, you see two dashed links. Let me see if I can get my cursor up there. There's a link going from Rockville up to the country and then up to a mountaintop near Frederick, Maryland. The building that this link is located on, we had to take everything off the roof to install a new roof. And so the new roof has been installed, but we haven't reinstalled the equipment on the roof yet. So that's why it's shown as the dotted line. It was running for several years, but it's off the air temporarily. And here's another link from a mountaintop near Frederick over well across the Pennsylvania line to another tower near York, Pennsylvania. And that link is actually 53 miles long. And it was in operation, I guess, for close to 5 years. It was one of the first links we put up. It's off the air right now, and we just haven't made arrangements to have a tower climber get up to see what's going on with the equipment. So it'll be back at some point, but everything else that you see here is working and has been working for at least 2 years. And here's the bad news. This is pretty sparse. The area that we're looking at here runs from basically the front range of the Appalachian Mountains around the perimeter to the coastal plain. From DC, Baltimore, and east is pretty much all flat land, less than 200 feet above sea level and almost no hills at all. So in between, which is kind of the heart of our built-up area, is rolling hills, what the geologists call the Piedmont region. And the Piedmont region is murder for getting line of sight paths. Almost anywhere where we have a hospital, it turns out that it's in a valley surrounded by hills. And so it's very hard to get from any of our hospitals or EOCs to get a clear line of sight path to any of these network nodes. So at this moment, we have exactly one hospital connected to the network. We have our eye on a couple of buildings that will give us pass to a couple of EOCs in this area, but the building owners have not yet blessed us installing our equipment on their buildings. We're not offering them big money to do so. We're kind of beggars, and it turns out that finding places to put these nodes is a real challenge for us. Plus, we're not salespeople, we're techie people. And there's a lot of places that this network needs to reach to that we haven't gotten to yet. And as I say, that's a disappointment, but it's one that we're working for. So we really need some more volunteers. We need volunteers with expertise in networking. We need some cybersecurity experts. We need some people who are willing to go out and make cold calls to building owners and real estate companies and say, hey, we're trying to do this for the community. Will you help us by letting us put a couple of these 2-foot dishes on your roof? We'll get there, I'm confident, but that turns out to be the hardest part. So I think I've probably already covered these points. We have right now functional nodes of 30, 40, and 50 miles, but ideally you want to be 25 miles or less, and 5 to 10 miles in a perfect world. As we get more sites, we'll have more way to link into more of our hopeful customer sites. We have quite a few hospitals that we've talked to and say, I'd really be thrilled to be on your network, but we just haven't found a way to get to them yet from the backbone. So just to give you a few kind of pros and cons, if there's enough AirMax nodes interconnected with multiple other nodes, then traffic can automatically reroute around a failed node. But as I said earlier, this routing capability has to be programmed in an AirMax network, unlike in a mesh network where it's automatic. The routers that we buy are all capable of being managed remotely over the network. So most of the time we don't have to go to the site if we need to change the routing configuration. We do it from the comfort of one of our homes over the network. Like a mesh network, the AirMax network doesn't scale well if there's too many users, because basically all of the links are in the same general amount of link capacity in terms of data throughput. So the more users you have trying to send data over the same link, the more contention you're going to have for the available data throughput on that link. So again, the more nodes that you add into the network, the more paths you have to spread the data out so that you don't have any bottlenecks. But one of the nice things about the AirMax concept is each of these point-to-point links can use different channels, so you don't have as much problem with the hidden transmitter problem, and you can have multiple radios at one site operating on different frequency bands, so that they're not interfering with one another. They can all talk at the same time, and they can all listen to their respective link buddy without interfering with each other. I've talked a lot about AirMax versus mesh, but mesh has some real advantages in terms of being easy to set up, especially in the field. And so you can use one of these point-to-point links or our backbone to join together two isolated mesh networks, combining the best features of both architectures. It's not one or the other. You can mix and match and share traffic between them. So that's pretty much as I want to say about the network. And I know people who are far more technical than I am about how to use the equipment and the configuration and so forth. So we're not going to get into that certainly in the next 15 minutes. But let's talk about what our customers, and I'll put that in quotes, can use this for. So the simple answer is anything they can do over the internet, they can do over our metropolitan area network, as long as they don't exceed the available throughput. And they do it with a user interface that stakeholders are used to dealing with, because they don't have to learn any special software. They can use their normal browser or an email program that they're used to, or video camera viewing software that they're used to. This is just it's just a LAN to them, and pretty much everybody today knows how to do data over LAN. At most locations, we're talking about 50 to several hundred megabits per second being available from that location to other network locations. And we can also provide access to the broader internet through our system to support critical needs. So if a hospital loses its local internet service, they can use our network to access the internet from 50 or 100 miles away to do their critical, internet traffic. We can't support the entire needs of a large hospital, but we can support their critical traffic through an internet access point that's geographically, quite a bit distant from the hospital. So let's talk about some Emcomm applications. So the obvious one is to provide backup communications among EOCs, hospitals, and other served agencies. And as I mentioned, we want the capability of being able to project internet service to a field staging area or a disaster site or a shelter, either from a central location or from the nearest point where internet service is available. So suppose we have a plane go down in the Potomac River Valley, where you're not going to get line of sight very easily to our network backbone. But if you can set up a pair of these dishes to any building nearby that happens to have internet service, then we can get local internet access or VoIP telephones running down at the location where people are working. So it doesn't even necessarily have to go to our backbone. We can take our equipment into the field and just set up a link from the place where internet service is needed to the nearest point where it's available. We have the capability of implementing live video coverage of the incident or providing situational awareness at the EOC over the network. And what most people working on disasters really want is access to a telephone. And so that's one of the key applications for us. And speaking of which, here is, just a customary office IP telephone made by Cisco, set up on my workbench. We do have an asterisk VoIP telephone system server set up on our network at a central location. We have phones that are currently operational at several of our MAIPN user facilities, and it will be installed at all future client sites. And you can pre-program these phones and set up extensions for them on the telephone server, so that all you have to do is plug them into a live network port at any of our network locations, and the phone becomes operational with its pre-assigned extension. And the beauty of that is that most of our clients know how to use this equipment to communicate. Now, normally this VoIP system we have set up on a network is closed, which means you can only dial other points that are actually physically attached to our network. However, should a client experience a telephone outage, we have the capability of connecting our network VoIP system to commercial landline telephone. I have a piece of hardware in my house so that I can plug the network VoIP system into my home landline. And I'm sure that would violate the terms of my Verizon contract were I to do that and be providing telephone service, to a hospital EOC. But in an emergency, I don't think Verizon would complain too much. And we have that capability not only at my house, but at several other points in the network. And at one point in the network, we actually have a business IP internet service that we can legally connect the phone line to. So that's one really useful application that we have up and running and have had for some time. It's interesting that number of our network nodes are co-located with repeaters, and one of the repeater operators has set up an auto patch on the repeater that is connected to our phone system instead of to the commercial telephone system. So a repeater user can access the auto patch using their HT or mobile rig and dial any extension on our system. And when our system is connected to the landline network, of course, then they can make an outside call. So that's up and running right now also. Now that everyone has a cell phone, auto patches are virtually obsolete, but the day is going to come when in any given area, the cellular service is going to be greatly impacted by some kind of a large scale fault. And all of a sudden that obsolete auto patch is going to be really handy again. And so we want to be prepared for that. You just can't afford to have commercial phone lines at all your repeater sites anymore. It's just cost prohibitive. But connecting to the MAIPN VoIP system is free. So that gives us a telephone capability that we can use for practice, and it gives us an emergency telephone capability on the day that we might need it. Here's another interesting application for the technology. We needed to set up a voice and WinLink FM VHF UHF station at a local hospital for a mass casualty exercise a couple of years ago. And the conference room used in the hospital for their emergency operating center was landlocked, which means that from the conference room, which you can see in the bottom two photos here, it was located on an upper level floor, far from a stairwell, and with very little access. I think there was one repeater we could reach from inside the room, but we couldn't get to the repeaters that we wanted to be able to use for the exercise. We also wanted to be able to run WinLink, and you weren't going to get very far with a J-pole antenna inside this room, inside the hospital. So what we did was set up a microwave network from the EOC, which did have a window to the outside, and we pointed that dish to another dish on the roof of an adjacent building. And up in the top left corner, you see Keith and I on a very icy rooftop, setting up a Kenwood TMD710 radio. And you can buy a product called remote rig that many of you have heard of, that allow you to separate the front panel of the radio from the radio unit itself over a Cat5 cable. And so we used one of those remote rig units, a pair of units actually, and instead of using a Cat5 cable, we used the microwave link. In this case, it was only about 200 yards, but it was 200 yards upward, so that by putting the radio on the roof with a decent, external antenna, we were able to access several WinLink gateways and be able to access all of the local repeaters. And the person sitting in the hospital EOC at the operating position had the front panel of the radio sitting in front of them in full control, so that we could simultaneously run WinLink on 2 meters and also be at the same time transmitting and receiving on a 440 repeater. And we've done that trick now in a couple of different places at different times. Sure, many of you have had this situation, and what you end up doing is setting up a crossband repeater somewhere outside the building to give you that, wider area access. And maybe you set up an RMS gateway node or a digipeater outside the building to give you WinLink access. But if you use a crossband repeater, you have to go outside to the crossband repeater to change what repeater you're using. So this gives you complete control of the radio inside the room, with the range of having the radio on the roof with a short coax run to a good antenna. And there's an article with the details of how we did that on our website. You can look it up, MAIPN.org. So here's a few other possible amateur radio applications. We can use the network as a link receiver to connect a satellite receiver to the main site. We are currently using the network to link several repeaters together, either directly or over the internet. We have one repeater site that does not have internet access in a fairly isolated location. So they're using our network to get to a point where we can provide them internet access. You can run repeater control channels over our network. As I mentioned, you can run a repeater phone patch to a remote phone line over the network. You can use the MAIPN network for backhaul for DMR and other digital mode repeaters, Echolink, so forth. You can do digital amateur television, streaming video over the network, lots of experimentation, lots of opportunities to play with technology and learn about technology. And it's a good tool for recruiting high-tech people into ham radio. So enough said there. How are we doing on time? Can I just go on? Pretty much that's the big picture, but I can kind of show you a few war stories of things that we tried to do that did or did not work. How are we doing?
You're doing fine. Keep going.
Okay, so I mentioned a couple of times that one of our objectives is to be able to project the network into an arbitrary location. So how about a field day site? So this was an experiment in 2016 to see if we could project internet access to a field day site at Washington Monument State Park on the Appalachian Trail in Maryland. And there was essentially no cellular service at the site. Certainly no landline capability. We had a couple of network nodes on a ridge about 10 miles east of this mountain ridge here. So 10 miles, that sounds really easy. Well, okay, but you look on the topographical map, and there was another ridge that was just slightly higher that was between us and both of those other sites. So no line of sight path to an existing backbone node. So, okay, there's a ham who lives further down the ridge that we're on, just a few miles actually. He has a farm. And so he said, maybe we can shoot down our ridge to his farm, and then that's far enough south that we can then shoot across to the east and get to one of our backbone nodes. So we set up a couple of dishes on a pole. You can see a farm building and a pasture out behind the fence there. He was grazing horses on that pasture that day, and they stayed far away from us. And from the lower dish, we had a very solid connection to our backbone site across the valley, Middletown Valley, if any of you knows the local area. A very picturesque place, by the way. And the upper dish was kind of pointed straight up to the ridge, kind of you see the little hill at the center of the picture, right at the horizon. Our field day site was right at the point of that ridge, actually maybe 20 or 30 feet below the ridge top. We can certainly see to where we're trying to get to, but it turns out that microwave signals at 5.8 gigahertz do not go through foliage. It doesn't take more than a few trees to completely kill the signal. So even though we got the dish at the top of the hill, shown here on the left, up 40 feet in the air, it was line of sight except for the trees 100 yards away. And we just didn't get enough of the signal to make it really usable. We could get a connection, but it was intermittent. It would work for a minute and then it would die. So we did not meet our objective. Basically, it was unusable. If we could get the dish at the farm up higher, or if we could get the dish on the mountaintop another 50 feet up in the air, then certainly we would have been successful. But the trick is you have to be able to get over the trees. So it was a good learning experience. It was not a successful effort. Here is the reason this photo is so fuzzy is it's number one, it was a very hazy day in the Catoctin Ridge of Maryland. But the other thing is this is a blow up of a very small part of a photograph. So we're here on a field adjacent to a local high school with an elementary school directly behind it, out of sight. We have a MAIPN backbone mode right up in the saddle of the ridge, where you can see the message saying approximate location of MAIPN Braddock Heights site. So we have at that location up there, you can't see it with this amount of resolution, but there is a mast that is above the tree line, barely above the tree line. And so it is literally a line of sight. Unfortunately, the trees in the near distance here are within the Fresnel zone of the line of sight path. This metal flagpole out in front of the school is also within the Fresnel zone. And what that means is that these physical objects that are conductive, it means that the path, while you can see it with a telescope, the signal strength is poor. So again, this field that picture was taken from was the finish line of a planned charity bike ride in Walkersville, Maryland. We scouted the site ahead of time to see if we could deliver internet and phone service to that site from our backbone up on the mountain up there. And with the equipment we had at hand, we just couldn't do it. We were pretty sure that if we could have set up a relay point on the high school just across the way, we would have had a good enough angle and enough elevation to have made the connection up to the mountaintop. But it didn't turn out to be practical to do that. This was during the middle of the summer. It was only 2 weeks to the event. The event organizers didn't think they were going to be able to get in contact with the school board and make the arrangements to get to that rooftop. So we had to say that we couldn't help them out for the event with our network. Now we might be able to with the equipment we have now, but at that time it was a no-go. And so the beauty of it was that we went up there ahead of time. We figured out that it was a no-go so that they weren't relying on us, and we didn't disappoint them on the day of the event. They found an alternative way to get the connections they needed. So then I think this is my last example here. I mentioned earlier that we've made a connection, that we have just one and only one hospital currently on the backbone, not for lack of trying, but this is the link path. And here we're talking about a link of just under 4 miles. And we're using software that is freely provided by Ubiquity, the hardware provider, on their website to do link planning. So this link planning software gives you a bird's eye view of the terrain, and you can turn on a satellite layer and see the Google Earth image if you choose to do that. And you can also show on the screen an elevation profile. So here we see the dish on the roof of the hospital about 70 feet above ground level, and that's a scale. You can see actually here the parameter 75 feet above ground level that we've put into this planning software, and so it's showing us the map. On a tower 4 miles away, we have a dish that we put at the 160-foot level, and it really looks like it's a way in the clear from the terrain. But you have to realize the trees in the Maryland grow to be about 100 feet high. So I actually exported this image from the Ubiquity website to an image on my hard drive, and then opened it up in drawing software and drew 4 trees that are each 100 feet high from the high points on the intervening terrain. And you can see that a 100-foot tree at this location, basically it completely blocks. It's not just partway in the Fresnel zone. It's blocking the entire radio signal. And the other sites that are more distant from the hospital are less and less of an issue. So now the question is, what's on the ground at this point? And so let me jump to the next slide. Here is a Google Earth view of that hilltop. Basically, the top of the hill, the flattest part of the hill, is the yellow circle here. And you can see that there is actually a clearing directly underneath the path between the two sites. So maybe we have a half a chance. There's a couple of trees over here. They're on the other side that are partway down the hill. They may or may not be tall enough to cause interference. So we actually do have a slight chance of making this path. And on that slight chance, we paid a climber to climb up 160 feet on the tower and install the dish to see if it would work. And one other thing I want to point out, when you're looking at this elevation, that red tree that I've drawn there looks awfully skinny, and you might say that really looks like it's out of proportion. That kind of fooled me too the first time I did this. But think about it this way: the horizontal scale of this drawing, we're only talking about 100 feet from here to here, but we're talking about 4 miles from here to here. So it's way out of scale between the horizontal scale is about 100 times more compressed than the vertical scale. And that's why my tree looks so disproportionate. But that's actually, that's actually 100 feet of height. So enough said about that. So nowadays, well, I guess I should finish that story, sorry. So we did set up the link. We are able to get about 20 megabits per second through the trees. So the foliage, we got a little bit lucky with the amount of foliage that's on those ridge lines. So we do get a usable signal. It's not nearly as much data throughput as we would like at our hospital. But until we get a better site to get a better line of sight path to that hospital from our backbone, it at least allows us to demonstrate the people at the hospital and anyone else who wants to be an observer that we can place a phone call from that hospital over our network. We can send email, we can do all the things that we talked about from that hospital, but we're limited to about 20 megabits per second. And that's still better than dial-up internet. It's a whole lot better than WinLink at 1200 baud, and I'm a big fan of WinLink, but 20 megabits per second, when we can get it with this kind of technology, gives us the opportunity to do things that we can't do on HF, and we can't do on a 2 meter 5 kilohertz FM channel. Okay, enough said about that. So we got very lucky and had this van donated to us, and were able to outfit it. And the key thing about this van is that it has a 50-foot telescoping pneumatic mast. And frankly, this truck is way more truck than we'd like to have. Not everybody can drive a truck this size. Not everybody is willing to drive a truck this size. We were lucky enough to have it donated to us in very good mechanical condition. We have a ham who's very generously supporting it by paying for the insurance and maintenance on the truck. And it gives us an opportunity to do testing of sites out in the field, making it very easy to get a dish, which is permanently attached to the top of the mast, up 50 foot in the air. And as I mentioned, trees grow to 100 feet. So there are still sites where using this equipment, we can't get over the treetops. But it is a very useful tool for checking out sites in the field. Sometimes 50 feet is enough. If you're on a hilltop, the trees in the distance, even though they might be 100 foot tall, if they're downhill, we can get over top of them. This was actually the site of an emergency preparedness fair for the public. And we got there several hours before the fair. So we were the first ones there. So you don't really see anyone else in the parking lot 3 hours after this photo was taken. There were dozens of agencies, the Red Cross, all of us, they were all around us. But we got there early to set up a microwave link. And again, 50 feet up in the air once we got the dish up. And it does have an as-L rotator, so we can move and point it wherever we need to. 50 feet wasn't enough to get us to the backbone, but it did get us to the roof of an adjacent building. And on that adjacent building, we set up a dish, which did give us a line of sight to the backbone. So here you see one of the, because we're only going over about a 10-mile link here, we use one of the lightweight, inexpensive dishes. You can actually see the radio there, or the radio and the router are on this model are mounted behind the dish rather than being built into the feed horn. But that's the whole thing, one Cat5 cable from here, in this case, to another dish on the other side of the roof, pointing down at the parking lot. So this link on the rooftop gave us access to our band backbone. And so we ended up with internet service down on the parking lot where the fair was. And we were even able to provide an interconnection to one of the other exhibitors at the fair. What else should I say about this? Well, one thing I did want to say is notice that there's a coil of wire sitting on the ledge here. And that is a real safety violation. If someone were to bump that off, it could give somebody down on the ground a real headache. And this points up to one of the other kind of people problems that we have, is that these sites that we're working at are technical sites, and we get volunteers helping us out. And the volunteers are not necessarily well trained in working at these technical sites. They don't know the safety rules. I didn't notice that someone had set that cable there until, well, certainly well after this picture was taken. And so when you're working with volunteers in these technical locations, you really have to be concerned with safety. And it doesn't hurt to have good insurance. And here, let me put in a plug for the ARRL's club insurance. Just Google it on the ARRL website. Not a bad deal. We haven't had to use it yet, and we hope we never do. And last but not least, a few other examples. Here, way up at the top of the picture here, it's a 200-foot tower. The climber is up at 160 feet. There was so much stuff on the tower that we couldn't get any higher. But we are the volunteers raising one of the dishes up to the climber and doing it safely. And the guy in the foreground here is using what's called a tag line to pull the dish away so it's not banging against the side of the tower on the way up. It was raining when we did this, but the installation went very smoothly. Unfortunately, we were less than thrilled with the results in terms of, trees intermediate in the path, but it's still, we call it a partial success. Just one other example of an installation. Our 2-foot dishes look like toys compared to the big boys. This one, the big one, would require a crane to install, I'm sure. We're about 200 feet off the ground in that photo, but well back from the edge. And we have our hard hats on, we have our safety glasses, and the crew on this particular day has quite a bit of experience working up here, mostly doing repeater installations. If you have those skills, then you can do this microwave stuff, no problem at all. So that's it for me. So the technology, I hope I've given you a flavor. Lem, you guys up on Cape Cod, I feel certain that that you'll be able to get over the trees and make some very useful links there. I actually went on Google Earth myself and had a look at your hospitals. It looks very doable in your location. Of course, if you're in, someplace where you have mountain ridges, just having the mountain ridge there is nice, but you have to have somebody with real estate up at the top who's willing to let you use their property. We found that the people skills are as important as the technical skills. It's really important to be guided by customer needs. Don't let yourself get frustrated by poorly written and incomplete documentation. Think of that documentation as a puzzle to be solved, and you can work your way through it eventually. Try and find someone else to help you. There's a lot of help on the internet. You can locate us via our website, MAIPN, Mid-Atlantic IP Network.org. my email, I have the ARRL net email, so it's kn3u@arrl.net. Have fun learning new things and trying new things. And that's it for me. Here's our call signs, there's our website. We have a bunch of folks working with us, but right now we're the three monkeys who are trying to keep this thing moving forward. And here's a few resources for you. And that's my last slide. So I'll be happy to entertain some questions, share.
Okay, that was very well done. Thank you, Al. I don't know, you might be able to make it on TED.
I don't know.
Okay, do we have, I don't see hands up. Barry, how are we doing in chat? Oh, I don't have a Barry. I see a note here in chat that Barry left. So we'll just have to take a look at chat and see what we got here. Mostly comments. Are the antennas affected by weather? Wind, snow, freezing, rain, yada, yada?
At 5.8 gigahertz, the answer is yes. I really don't know in great detail. There are some microwave bands that are very, that are right at what a resonant point for the water molecules, where a little bit of rain kills you completely. We have a very heavy rain causes us to fade. A heavy snowfall might, but I haven't certainly experienced that. We find that, if you can get over the trees, you're going to have 99.99% reliability.
All right.
And I'm truly, that is a non-expert answer.
But it's an answer. We can deal with it. Okay. Thomas Horn, he offered to add some slides and examples of the service event. I don't think we have time for this one. We might be able to pull that into another presentation. So get in touch with us if that's something you'd like to do. And Tom up here says that the fact that 2.4 gigahertz allocations are mostly unusable in that environment, best choice would be 3.4 or 5 gigs. You got?
I agree.
Okay. Okay, looks like that's pretty well. I don't see any others. So if I'm missing a comment or a question here, jump in there and let me know. Again, no hands are showing. The presentation went long. We don't mind long presentations when it's a continuation of what's really, really good. So appreciate that, Al. You did a great job.
Thank you.
Okay, and Lynn, thank you for giving us Al. Appreciate that.
Well, thank you very much, Al. I appreciate you coming and sharing with us. This is good information, and I hope everybody enjoyed it.
Well, the pleasure is mine, and I love that scenery behind you. Wish I was with you.
There's your ocean, Dan.
All right. Anybody got anything? You want to make a comment? Okay. With that in mind, folks, I'm going to call it 73 for now. 73 is everyone. And again, thank you for attending.